All right. And we are now going to talk about dimensionality reduction, which is our second lecture. And it's, again, heavily different than the sequence that you see in the book, as always, because I don't like the sequence in the book very much, as I've said before. and I think clustering and dimensionality reduction, in my opinion, are two very interesting introductions to data mining when it comes to people who have been taking machine learning courses, because it's more or less familiar. The next things that we're going to see, like when we start seeing things like networks, streams, and things like that, then it goes a little bit farther away from what we're used to do, especially because the input is not just this structured data in a table anymore, right? So far, we've been using as inputs to our algorithms normal structured data that's just in a table, which is still the case today, but in some future lectures, we won't do that anymore. We're going to start looking at other types of data, like networks or streams. And then that's going to move a little bit further away from what you're used to. So I'm decided to start from this because it's a bit more familiar, I guess, and more common also. And I hope that it works. As we talked in the previous lecture on clustering, there are two main types of unsupervised learning, or just like learning from the data without having labels to confirm whether your results are good or not, right? And that's what's like unsupervised is. We dealt with clustering. It's for some reason it's inverted here, but we dealt first with clustering, and now we're going to deal with dimensionality reduction. And this is one example of a 2D dimensionality reduction of a data set. That's from this website over here. This is called TSNE. It's a very advanced algorithm that is more or less the state of the art nowadays. I mean, some people try to contest it and to come up with new ones. And I mean, fine, but TSNE is still a very heavy name on the dimensionality reduction research. And this is the visualization of that very classic data set, the MNIST, which is a bunch of handwritten digits. So digits like numbers that people have written by hand, I guess you know. And then they have these pictures, and then the challenge is to try to separate them into the actual numbers, like zeros, one, twos, and so on. And this is what TSNE does. It projects, very simply, it projects the data into 2 dimensions, so X and Y. And then you can visualize that, because when you have 2 dimensions, it's easy to visualize. So then when you visualize that as a scatter plot, simply by plotting the points in the X and the Y axis, then you see that the digits, well, each digit here is one color. And you can see that they're quite well separated. Not perfectly, nothing is perfect. Like, for example, this group here and this group here, they are intertwined, for example. And there's lots of noise spread around the projection, but it's very good, especially when you compare this with some other results. So this is one example of what a dimensionality reduction algorithm does. But I will start talking about this thing called the curse of dimensionality. And I like to define it, although very few different people define it in different ways. My own definition from 2018 is that things get weird in high dimensional spaces. Basically, that's how I like to think of the curse of dimensionality. And you will see in the required reading, you have a section on the curse of dimensionality, which is interesting. Actually, 2, 1 in each of the books. Both books talk about the curse of dimensionality in different ways. So that's why I like to define my own version, because everyone talks about it in a different way. But basically, that's it. Things get weird in high dimensional spaces. So things that we consider as, let's say, straightforward or obvious when we're thinking about 2 dimensions or 3 dimensions, especially when it comes to Euclidean distances, which is the normal distance that we always compute, right? Like, what's the distance between 2 points is always a line between them, and the length of that line is the Euclidean distance. So we think of that as being, let's say, the obvious way of computing distances. But the truth is that as you have more and more dimensions, the distributions of points in these high dimensions, they start to behave in ways that are not obvious and how they say, not straightforward, not easy to interpret, not easy to understand. There are many ways to exemplify that, but I chose one that's like a little bit simpler to understand. Or I hope it's a little bit simpler to understand, because I'm not using heavy math. If you want a more formal definition and proof, then look at the books, at the required and the optional readings, and you will find much more formal descriptions of this. But I want to give a more intuitive one. So let's say that you're training some machine learning model. In this case, we can think of machine learning models in general. It doesn't have to be unsupervised learning. And you have some specific amount of data, right? Especially you have an amount of training data, which is just data that's available to you. And this data has features that cover the things about the data points that you want to train on, right? So in this case, let's say we have dogs and cats, and we're trying to differentiate between dogs and cats. And let's say they're pictures. It could be pictures, or they could be some form of, let's say, description of these dogs and cats, right? As long as there are features, some features. Now, the interesting thing here to understand from this picture is this: if you had just one dimension, let's say you just have one measurement of your cats and your dogs, like the height. Let's say you take a bunch of cats, a bunch of dogs, you measure their height, and you say, okay, this is the only feature that you have. Go and try to differentiate between dogs and cats. That wouldn't probably be very accurate. Like, one dimension is not much. So, but the truth is that there's a certain space of possibilities in this one feature, right? I mean, there's some minimum sized dogs and cats, and there are some maximum sized dogs and cats, right? There's a certain range, so to speak, of values or distribution of values in this specific feature of height, right? It's not random. You don't have dogs with all sizes and cats with all sizes from 0 to 100 meters. There's a range. Okay, so let's just stick to the fact that there is some range in a feature. Now, if you want to, let's say I want to cover 20% of this feature range, right? I want to make sure that I have a very good substantial sample of all the possible heights of cats and dogs, because I want my data set to be representative. Now, if you wanted to cover 20% of one feature, then obviously you would need 20% of, let's say, all the possible values for height in the world, in all cats and dogs that exist, right? Let's say. Then that's what this little red area here represents, right? Now, okay, that's straightforward, because that's just one dimension. So I would need 20% of everything, all possible values of a feature, if I wanted to cover 20% of the range of that feature with my data. So let's say I'm gathering data, right? I'm gathering information about cats and dogs. Now, if I have two features, then that becomes like a square like this, right? So I have a certain range for the first feature, and I have another range for the second feature, and I have a combination of all the ranges for both features. So every dog and cat will have height and, let's say, weight, right? So then I have a range for feature one, I arrange for feature two. So a range of heights and a range of weights. Now, if I wanted to cover 20% of this, again, like, let's say this is just a theoretical exercise. If I wanted to cover 20% of all the combinations of weight and height in cats and dogs, then 20% is not enough anymore. I need at least 45%, let's say, of each of the two features in order to get this little red area here, where this red area here represents 20% of the area of the entire, it's not 50, you see, or else that would be 25%. It looks like 50, but I guess it's not really accurate, but it's 45. So that represents 20% of the area of the entire square, because the area of the entire square would represent like all possible combinations of weights and heights in cats and dogs, period. And to cover 20% of that, I would need to sample, let's say, at least 45% of the range of one feature and 45% of the range of the other feature, and make sure that the combination would really like be diverse enough to cover this. But that's just a theoretical exercise. And this keeps growing as we have more dimensions. So for example, if I had now 3 dimensions, weight, height, and let's say length, horizontal instead of just vertical, then again, I would say, okay, I want to cover 20% of the feature range of all combinations of weights, heights, and lengths, because I really want my data set to be very, very, very representative. Well, in that case, you would need at least 58% of the range of each of the features in order to form this red cube here, which in this red cube here represents 20% of the entire possible range of combinations of features, okay? So theoretically, that is unfeasible because you can't really sample so many things. You can't really go out there and sample 58% of all the possible ranges of every feature that you extract from a dog, right? Especially because, for example, if you have images, then you have hundreds of features. And this is what happens. Let's say this is the kind of thing you're looking at as the dimensions grow. So for example, when you go around 20, let's say you have 20 dimensions. So if you really want this to have, let's say, a representative sample of this data set that you have, of this population that you have with 20 features, then you would have to go out there and sample like more than 90% of the range of every feature in your data set. And I mean 20 features. So that explodes, right? And at some point it kind of stabilizes a little bit, but it doesn't matter because that's unfeasible anyway. And anyway, what happens is that you don't really have the, let's say, the ability of sampling new points anytime you want, right? What you have is you work with the points that come to you. So if you have 10,000 points, then you have 10,000 points. You don't have the ability to, let's say, go out there and get more points anytime you want. And even if you did, you wouldn't be able to gather so many data points. But the point is that whatever data set you have with 10,000 data points or 50,000 data points, the more dimensions you have in your data, the less representative that set of points is. Because the set of points is fixed, but if the dimensions go up, then considering what it means to have a representative data set, in this case, that specific amount of points that you have becomes less and less representative the more dimensions you have, because there are so many possibilities of variance, so many, let's say, axes for the data to vary, that those points that you have, they become less and less representative, so to speak. So the takeaway point here is that you can't have more points, right? You cannot sample more points until you have a representative data set. That's not possible. So if you cannot have more data, then you need less features. Because if you can represent the same patterns that you have in a data set with 20 features, if you can somehow reduce it to 5 features and still have most of the patterns that you used to have before with 20 features, then that will be much better. And this is an interesting representation where it says classifier performance against dimensionality. This is from this article here, The Curse of Dimensionality and How it Affects Classification. So if you're curious, you can also just check this, this source here later. But I don't remember exactly how they got this, if it was experimentally or theoretically. But depending on how many features you have, your classifier will go down. So as the dimensionality increases, the classifier's performance increases until a certain optimal number of features is reached. Further increasing the dimensionality without increasing the number of training samples results in a decrease in classifier performance. Now, of course, this is not just like every data set in the world needs to have this number of features. This is specific to the data set, because again, this is a theoretical exercise, right? I'm theoretically thinking that all features that I have here, like this one, and the other one, they're all like varying perfectly throughout their axis, and that all the combinations are important. That's not the case. And this is actually the point, the most important point, because even if you have 20 dimensions, like for example here, I don't know, 0, 1, 2, 3, 4, 5. So this is 20, I guess. Yeah, 5, 10, 15, no, 25. This goes up to 25 here, right? So let's say you have a 25D dimension data set. But actually, there is some hidden, let's say, optimal number of features that would almost perfectly represent the data set, but it's hidden inside a 20D data set, because for some reason you gathered these 20 dimensions just because you could, or just because they came from somewhere, or because it's an image, for example, right? So an image has lots of pixels, and every pixel could be a feature in some models. But not all the pixels in this picture are important for the classification. So the real dimensionality is hidden inside this big, like, dimensionality, this data set with lots of dimensions, and you don't really know what is the optimum. Most of the time you don't really know. And feature selection is one alternative. Feature selection is simply like, okay, I have 3 features that are very good, that that really are very representative to my data set, and I just take these 3 and throw away the rest. That is one alternative. But the truth is that usually that's not that good. Why? Because the actual optimal features, because there are 2 things, right? One thing is the number of optimal features. The other thing is, what are these features? Let's say you for some reason have established that the optimal number of features for a data set is 3, because anything other than that is just adding noise, or it's redundant, right? So it's redundant information that you already have, or it's just noise and it's actually getting in the way. However, those 3 dimensions that are the optimal dimensions, they may not be actual dimensions from the data. Maybe they are not explicitly represented there. Maybe these 3 optimal dimensions that you have, they are actually combinations of the existing features. They're hidden in a combination of the existing features in such a way that you could extract them. If you could extract these 3 optimal features by combining the existing features somehow, then you would be generating these 3 new features, and these would be the best possible 3 features for your data set. And then you could safely say, okay, I found this latent, let's say, factors, these 3 latent factors in my data, and these are like the 3 best features that I have, and now I will work with this data set with this many features. So more or less, this is the motivation, right, guys? First of all, because the original dimensionality may be too much, so it does not represent the actual, let's say, patterns of the data, so you want to reduce that. It's better to reduce than to select features most of the time, because maybe the patterns are not explicit in just the raw features. So you need somehow to beat the curse of dimensionality. Since you cannot sample more points, you need to reduce the features, because then the fewer features you have with the same number of data points, the better representative, let's say, your data points are, right? Of course, you lose information by doing this. So the idea is that you try to lose as little as possible. Yeah, okay, and this is just an example of what I was talking about, because I say, well, feature selection is one alternative, but actually sometimes the data has lower intrinsic dimensionality, which means, for example, in these two cases, these are very simple examples of intrinsic dimensionality in the data set, which is that these are 3D, right? So these are this is a 3D Swiss roll, as we say, and this is a 3D S curve, right? So they're 3D, as you can see, there are 3 axes here. However, if you look at them and you realize that actually these things are just rolled up structures. This is a rolled up structure, like a plane. It's like a piece of paper that you rolled up, and this is also like a piece of paper that you twist into an S. You could see that, well, you know, this actually is actually a 2D structure. If I took this S curve and I how do you say that? I don't know, spread it, that would become one, let's say, flat piece of paper, so to speak, or a flat something, a rug or something. You put it in the ground, right? So this is what you do when you roll your rug to carry it somewhere else, and then you spread it again, and it's a 2D surface, but it's rolled up in itself in a 3D space. So if you could somehow understand or detect the fact that this Swiss roll is actually a 2D thing that's embedded inside a 3D data set, then you could extract these 2 dimensions, which are completely new, right? I cannot just take 2 dimensions from this data set, 2 combinations of existing dimensions here. I cannot, and get this spread out rug. I could not do that. So I need to detect these dimensions. I need to somehow reduce the dimensions into 2, but not by throwing 1 dimension away, but by generating 2 new dimensions, right? And this is what dimensionality reduction algorithms do. Okay, that was long. So let's see how it works now. We're going to talk now about dimensionality reduction. This is a very nice little picture from this book. An eternal golden braid, and this is interesting because it's a 3D structure that, if you look at it from different sides, you see different letters. I mean, you don't see them very clearly, but if you throw a light on them, they reflect with different colors from different sides. So that's an interesting way of thinking about this different dimensionality thing. So basically, a very simple abstraction about dimensionality reduction that you should reproduce in your framework. Think of the R as a function. It's this function over here. It takes a data set that has n data points and p dimensions. Then it does something to it, and it spits out a new data set that has still n data points, the same number of data points, but less dimensions. Like, for example, here I went from 1, 2, 3, 4, 5, 6, 7, 10 to 4. So we reduced a 10-dimensional data set to a 4-dimensional data set, right? And since it's dimensionality reduction, we always expect that Q is significantly lower than P, like much lower than P. Sometimes you go from 3 to 2, but that's usually just exercise. Most of the time you go from 100 to 5 or something like this. And the goals of any of these, and there are many of these, right? So it's a function, but what the function does exactly, it has hundreds of different options for that. But the goals are more or less the same for all functions. They're general goals: to map high dimensional data onto lower dimensional representations that may be more easily manipulated and visualized. So visualization is one very common use, which is you try to make it, to reduce the data set all the way down to 2 dimensions, and then you just plot them in a scatter plot, and then you visualize that. preserve as much as possible the structural properties of the original space. So exactly what structural properties mean is open, because there are many different perspectives on the kind of structural properties that you want to preserve. And different functions or different methods will preserve different structural properties. So it's always a trade-off. You cannot just go from 100 to 2 and expect to have a perfect representation of your data set, because that's not going to happen. I mean, if you have 100 dimensions, then at least a little bit of variance, you have at least a little bit of variance in all the 100 dimensions. So it would be theoretically, let's say, impossible to have a perfect representation from 100 dimensions to 2 dimensions and expect that it's just perfect. It's not going to be perfect. So there's always a trade-off. And then each function or each method chooses a one specific structural property to maintain, right? So it could be covariances between the dimensions. It could be distances between points. It could be neighborhoods of points. It could be to maximize clustering performance and so on. There's almost always error, but it's useful anyways. And I like this quote very much. This from this guy Box, who wrote a very nice book on statistics and experiments and everything. And he says, all models are wrong, but some are useful. And this is a very good quote, because all models are wrong, no matter how good, no matter if you have the best possible neural network that exists, there will always be a little bit of error on it. But some are useful. So if you understand, if you accept that there is an error, then you can use the model for something. Like, for example, I accept that my dimensionality reduction method generates some error, but it's good for maintaining neighborhoods, for example. So if you use it for the specific goal of investigating neighborhoods, then it's okay. But if you take a dimensionality reduction that preserves neighborhoods, and all of a sudden you start looking at the covariance between the features, then you're doing it wrong, because that covariance was just not preserved, at least not in as a rule. So there's always errors. But there are many motivations of why you would like to do it, like pre-processing. So you can reduce the dimensionality before training a classifier, for example, to try to beat the curse of dimensionality. You can try to minimize the impact of outlier variables, confounding factors, so things that are in the data but not necessarily helping with the main patterns that are in it. You could do feature engineering, which is really interesting, because you could test if a set of proposed features describe the data in a satisfying way. So let's say you're trying to create some, engineer some features for your data, and you know a little bit of what to expect. So you can use this in order to test so you can reduce the dimensionality. Like, for example, let's say you have 10 features, but you know that these 10 features are actually representing some patterns that are actually two-dimensional. Then you can do this and test if the 2 dimensions still represent the things that they should, let's say. So that's something that it's done, for example, in the how do you say, the planning or the design phase of a machine learning pipeline, right? For example, if you're working in a company and you have a lot of data and you're trying to somehow engineer a set of features for running a classifier, but you're not sure if these set of features actually are good enough, so you can use that dimensionality reduction to investigate that, and that's really interesting. I've seen some interesting examples of that. And just visualization to explore the data to find patterns that were not initially apparent. So again, if you have 100 dimensions, then obviously you cannot visualize that. But if you reduce them to 2, then all of a sudden you put them in a scatter plot, or even 3 if you're using 3D visualization or computer graphics, then you can all of a sudden see some patterns that you had no idea were even there. And information visualization. I'm going to skip this a little bit simply because you've seen so much information visualization, and these slides, I've used it also to teach this to people who are not used to information visualization, but you have seen this a million times, so I will not really focus on this too much for now. I'm just going to skip this thing. Now, remember, this is unsupervised learning. So labels are not used when doing dimensionality reduction, okay? And this is this kind of a caveat that I always add this when I have students who are coming from machine learning courses, which is the case here. So always remember, it's unsupervised learning, no labels. It's the same with the clustering, no labels, okay? They may be used for checking the accuracy of the results if you have them, but that's it. You should never use them as part of your optimization process. And now we're going to talk a little bit about the similarity measures, linear algebra, gradient descent, lots of math. So please don't get depressed. Actually, I'm going to try to be very, very light on this. Let's see if I can succeed on that. So we start with what's possibly the simplest type of dimensionality reduction, which is just linear dimensionality reduction. So what is a linear dimensionality reduction? Our linear methods are those that work by doing a linear transformation on the original data in order to go down to how many dimensions you want to have, right? So the goal is to find Q orthogonal vectors, which are themselves linear combinations of the original features, such that after transformation, some structural properties are maintained. So we are looking for, it's almost like it's a change of base, if you will. But it's just that usually when we think about change of base, you're thinking about maintaining the same dimensionality, but with different axes, right? In this case, we're changing the base, and we're also throwing away some of the new dimensions. So let's say you have a certain data set that has a certain base, and then you change it to a new base, keeping the same dimensionality, and then you throw away some of these new dimensions for using some kind of a criteria to choose them. And we're going to look at that in a few more details. In this case, any linear dimensionality reduction method is a transformation P that goes from a certain P dimensional space to a certain Q dimensional space where Q is less than P, right? And this is the framework, let's say the linear algebra framework that you use, because you have a certain projection matrix. And when you multiply that with any data point from a P dimensional space, you end up with a data point in a Q dimensional space. So this projection here is Q by P. This one is P by 1. So you end up with a Q by 1 vector here, okay? And so the point here with the linear method is that you need to determine this matrix here. This is the matrix that you're looking for, with the coefficients to be able to transform any data point from the original dimension, the P dimension, down to the final dimension, the Q dimension. So this is what, let's say, the linear projection looks like, a bunch of coefficients. And these coefficients are basically the way that you mix up the features that you have originally. So I mean, if you are a little bit familiar with linear algebra, you can see that every row of this projection P has a set of coefficients that will combine linearly the existing features in the original space to come out with just one. So there are coefficients for the first one, and then there are coefficients for the second one, there are coefficients for the third one, and so on. And all of them are linear combinations of the original features. And then that gives you new features. And maybe that's a little bit confusing, but let's see if it gets better as we go. The usefulness of a projection depends on its goals, right? So there's no final like one projection that works for everything. So for example, let's say you have a data set like this, right? There are two possible projections that are orthogonal, as we say. An orthogonal projection is a projection that just, let's say, it's just a shadow of the data on one axis. And like, for example, in these cases, we have two possibilities for these orthogonal projection. We can either look at the shadow of this data on the x-axis, and that would be this here, or we could look at the shadow on the y-axis, and that would be this one. And then you might think, well, which one of these is more useful, right? Like, let's say I have an algorithm that only works with one dimension. So I have to reduce because my original data set is 2 dimensions, right? So I cannot use 2 dimensions, all right? I have to reduce. So if I have to reduce, then which one of these would be more useful? Well, it depends on your goal. For example, one possible goal is to capture as much as possible the variance of the data. So I know that I will lose some variance because I'm going from 2 to 1. So I will lose some variance, period. But my goal is to capture as much as possible the variance of the data. So in this case, this one is better than this one. Because as you can see here, I mean, of course, I didn't compute the variance here, but if you do, then you will see that this has more variance than this, because this is more spread out. So the error here regarding the mean is larger than this one. So if you had to reduce from 2 to 1 in an orthogonal projection, and you want this to have as much variance as possible, you would use this projection. You should use this projection here, and not this one, because this has more variance than this one, right? So this kind of like represents the variance of the original data set better than this one. If you have to choose, I mean, both are important, but you have to choose. So you would choose this one, for example. Now, suppose that you actually have labels, right? Suppose that you actually know that this is a cluster and this is another cluster. Now, think again. What if my goal was to capture the division of the data between the two groups, not the variance anymore? Because the data is not, the division between the groups does not necessarily reflect the variance. So in that sense, this one would be better, because if you look at this one and if you look at this one, then you see that the separation between the groups is much clearer here than it is here. Because here the groups are intertwined. There's a lot of points on top of each other. So there's a lot of mix up. While here, if you were to actually like compute the silhouette, for example, you would see that this one here has much better separation between the two groups. So you see how you change the goal of your optimization, so to speak. In this case, it's not optimization, but it's just an example. You change a little bit, and all of a sudden you have two different projections, which are both good in their own way. So this is what different dimensionality reduction methods do. Some of them will prioritize something, some of them will prioritize something else. And that depends on what you want. For example, PCA is the most common one, right? It's very old, like it was proposed in 1901, but it's super used yet because there is such a strong theoretical foundation behind it that it really tells you, look, this is the best possible projection you can have, given that you are willing to, let's say, or if the limitations, the constraints are not a problem for you. And it can be summarized in this one simple sentence. It's the orthogonal projection. So as we've seen, an orthogonal projection is just when you just look at the shadow of the points on a certain axis, but not on the original axis, in the eigenvectors, in the M eigenvectors. The M here is just as much as you want, depending on how many dimensions you want to have. So you take some eigenvectors of the covariance matrix, which have the largest associated eigenvalues. I know that's like, yeah, it's one simple sentence when you understand it, but of course, maybe it becomes a bit confusing if you don't. So, oops. So very quickly, let's take a look at this data here. The goal, so the goal of PCA is to maximize variance, okay? The goal of PCA is not to separate groups or anything like that. It's just like this. Okay, you need to reduce the dimensions of your data set. So if you want to have the best possible representation that keeps the most possible variance from the original data set, then PCA is the way to go. It's not guaranteed to have patterns. It's not guaranteed to have clusters. It's not guaranteed to have even, especially non-linear clusters. But theoretically, it's the best possible projection. And I will explain to you why. Suppose that you have this data, and this is the original two-dimensional data, right? And let's say we want to reduce it to one dimension, as we did before, but we're not going to do like orthogonally by looking at the shadow on the x-axis or on the y-axis. We're going to look for a new axis. And we want to go from 2D to 1D. So the final representation must be one-dimensional, right? And we're going to look for a new axis for this data. Now, suppose that we start from this new axis here, this line over here, right? For some reason, randomly, let's say, we randomly choose a new axis, and this is the one. Now, if we look at the shadow again, the projection, whenever I say a projection, I'm talking about the shadow of this into the axis, right? So if we look at the shadow of these points into this new axis, then you can see that there is some variance here, right? It goes from here to here, not necessarily just the width of the variance, but there is some variance, more or less not uniform, but very, very diverse inside this range here. So this is a 1D projection, which means I just took the points and splat them into the new axis here. This is one possible projection. Is it the best one? I don't know. Probably not. It's just one of them. This is another one. I just took this line over here. So that would be like my new axis. And then again, I took the projection of the points into this axis. And this is the variance that I got here, right? So as you can see, depending on the axis, so depending if I choose this one axis like this, or this one axis like this, I get different variance. So this one is much worse than this one, you know, because the variance here is small, while the variance here was large. So if I do this, and if I keep looking for the best one, let's say if I did this iteratively, and I started with something, and I tried to improve it as much as I can, one iteration after the other, like doing a gradient descent, for example, then this is more or less what you would have. So you would start from some axis, and you would improve until you found the direction of maximum variance, as we say. And the direction of maximum variance is this one. So you can see that if this is the new axis that we choose, this line that ends up being the results of the optimization here, if this is the axis that you choose, this is the best 1D representation that you could have of this data that has the maximum possible variance. So it's this diagonal that cuts through the data. So then you take this diagonal, which is the direction of maximum variance. You project all your points. So you take this orthogonal projection, this shadow of the points, into this axis, and that's your PCA. That's your 1D PCA, from 2D to 1D. And again, and for example, this is the same thing, but this would be from 3D. So the left-hand side is 3D, and the right-hand side is 2D. So if we were to take a projection from 3D to 2D, this is more or less like how it would look in 3D, and this is what it would look in 2D. So you can see that the picture kind of stays the same, but it's splatted on 2D. And of course, in order to really see this as a 3D thing, you would have to kind of like rotate it, because as it is here, you can't really see it. But actually rotating is a good abstraction for what PCA does. For example, if you're going from 3D to 2D, PCA would be the position of a camera. If you take a camera and you position it in different ways while you're looking at the data, then PCA would tell you what is the optimal position to put the camera so that the picture that you get has the best possible picture of the data in terms of variance. In terms of variance along one axis and the second axis, orthogonal to the first one, like this. First PC, second PC, principal component. First principal component, the single direction that has the most variance in the data. Second principal component, the second direction, but it has to be orthogonal to the first one. It's not just any direction. It has to be orthogonal. Actually orthonormal, but anyway. So this is what PCA does. PCA will find the best possible angle of your camera, such that when you take a picture of the data, it has the largest possible variance. And this is actually, this is not the same as linear regression. Maybe some people sometimes make that confusion, but you see linear regression is not an orthogonal projection. It's like this projection on the direction of a certain axis, because it's supervised. So You're trying to fit one variable into the other, and with principal components not supervised, so we don't care. We just combine variables. It's slightly different. The general steps are these. You compute the covariance matrix. What's covariance matrix? It's a matrix where every let's say cell of that matrix is a covariance between two dimensions. So for example, if you have 10 dimensions, then you have a matrix that's 10 by 10, and each cell of this matrix is one covariance between a certain feature and another certain feature. So for example, the first cell 0, 0 is the covariance between feature 0 with itself, which is just variance. Then the second cell, like 0, 1, is the covariance between feature 0 and feature 1. And the cell 0, 2 is the covariance between feature 0 and feature 2, and so on. Pairwise covariances. Like a distance matrix, but instead of distances, it's covariance. Then you have to decompose this into eigenvectors and eigenvalues. I'm not going to go into that. There's information about this in the books. This is way out of scope for us to like how to do eigenvector decomposition. That is not something we will deal with here. There are methods to do that, but what matters is that a covariance matrix always has eigenvectors and eigenvalues, so you don't have to worry about, oh, is it even possible? Yeah, it's always possible because it's square and symmetric and real, so it always has eigenvectors. And then you decompose it into eigenvectors. Then you choose the Q eigenvectors with the high associated eigenvalues. These eigenvectors of this covariance matrix that have the highest, the largest, let's say, eigenvalues, these are your principal components, or in other words, the new axis that you're going to use to project your data like this. So the first principal component, the second principal component. So this is just the first eigenvector, or the eigenvector of the covariance matrix that has the largest possible eigenvalue. And that's it. Then you orthogonally project into the principal components. In this case, an orthogonal projection, always remember that it's like the shadow of the points into a certain direction. And there is some math here if you are willing, if you want to try to implement this yourself. This is implemented in every possible math library that exists, so I won't write. It's really simple, and actually it's not done like that with gradient descent like I showed in the picture. That was just for illustration. It's done, I mean, eigenvalue and eigenvector, sorry, decomposition is done with linear algebra methods that are not really, doesn't matter right now. I mean, there are naive ways of doing it, there are advanced, fast ways of doing it. So, but basically, this is the covariance matrix. I'm just going to skip a little bit about this because this is like eigenvectors, eigenvalues. This is stuff that you see in linear algebra that's not really that important to us, as long as you understand conceptually what it means. But basically, yeah, decompose it, choose the principal components, and project. And again, remember that we had this schema, let's say here in the beginning, of what a linear projection is. So this is how you find the coefficients. The coefficients here are the eigenvectors, and that like eigenvector number 1, eigenvector number 2, and then you will actually, yeah. So you see, I forgot I had this. So first principal component is this thing here. Second principal component, and so on. And then you take the first principal component, dot product with your data point, you get this first guy over here. Second principal component, dot product with some data point, you get the second element here. And if you're doing a 2D projection, that's all you have, right? You only have first PC and second PC, so that's all you have on your P. And then by multiplying this with any data point, that will straight away give you the actual 2D projection, because you will have then this Y guy over here. It will have 1 and 2. That's it. That's a 2D point. And you just do this with the entire data set. Q with PC if you have more than 2. And this is from the book, from the statistical learning book, that is showing what happens when you do a projection from 3D to 2D, right? And that's what is happening here. Like you have let's say you have a 3D data point, like a data set like this, and then you find this first principal component, you find this second principal component. Since you have two things, that forms a plane. And then when you put that plane in your data and you project your points in there, that's what's happening when you to end up with this 2D representation over here, right? So this is what you see from the original 3D data set, and that's because this is like the shadow of your points onto this plane that was formed by the first and the second principal component. And this is theoretically the best possible Q-dimensional approximation of the data. So this is the best possible two-dimensional approximation of the data, considering the Euclidean distance and considering, you know, the squared error. So the sum of the squared error. You can prove this, that this is the best possible representation that you can have when it comes to error, the sums of the squares of the errors and Euclidean distance. Although this does not mean that it's always the best one for extracting patterns, and that's what we're going to discuss next. So the good thing about PCA is that it's simple, it's fast, sometimes it's informative, it's very well known, heavily studied, it's theoretical, the theoretical foundations are very strong, but it's usually too simple for complex real world data. So if you're going for a complex and real world data sets, then usually you don't really see patterns that well, because complex real world data is highly nonlinear. And PCA cannot really see the patterns in these things. It's like this. Consider that you have a 3D data set that's so complicated that no matter which way you look at it from the camera, you can never really see the patterns. Like, consider that there are lots of nonlinear patterns, let's say, interconnected with each other in very complicated ways. No matter which angle you use to take a picture of that, you will never really see the whole thing at the same time. And this is what happens with complex real-world data. You have many dimensions; they're all interconnected in very complicated ways. So no matter which angle, so to speak, you look at this multidimensional data at one single point in time, you don't really see the patterns completely. So the direction of the largest variance do not necessarily translate to the most discriminative projections, to the best projections in terms of highly complex nonlinear patterns. There are some observations here on whether you should or should not normalize the data. So for example, or rescale, let's say. So the point here is very quickly that if you have features that are very different between each other, like for example, this is a data set that has some I think some cities. I think each point here is a city, and there's like some measurements on that. So in terms of crimes, right? So murder, rape, assault, and the urban population. So for example, 209,000, I guess 209,000 people in this city. I don't remember exactly, but I guess that's it. And then there's some or countries. Now I don't remember. It's in the book. It's been a while since I checked it last, but it's you can check it later. But the point here is that you have variables that are very different in scale. So one is like 18, the other is 87, the other all of a sudden is 6,945. So what happens here is that, as you can see, when you have the PCA here, it's kind of like this squeezed projection, because each of the dimensions has affected the let's say has affected the final results in very different ways. So then it's kind of like not optimal. And if you scale them down, for example, so you take all the columns and you just normalize them between 0 and 1, for example, either normalize them by the standard deviation, or you just rescale them down, for example, between 0 and 1, So then all of the features basically have the same range, so they affect the results equally. And then you get something more interesting like this. And these are the more or less the direction of influence of each feature. And you can see in this case that they are much closer to, they have more or less the same, let's say, influence on the results, while here the urban population and the assault had much larger influence in the results than rape and murder. And murder, you can't even see it because it's so small, and rape, it's very small like this. So this is not optimal. Usually what you want is for all the features to influence the layout in the same way, because unless you have unless you know that some features should influence the layout differently, right? But if you have no assumptions, if I have no idea, then you should try to make it so that all the dimensions will influence the layout in the same way. So I would say it's almost always good to normalize or rescale the data before you apply dimensionality reduction, unless you have specific reason not to.